Today we are going through some hints, okay, to how to approach the questions in assignment 6.3. This assignment mainly is on Newton's second law and Newton's third law of motion. Okay, just a quick recap. Newton's second law states that the net force acting on the object is equals to the mass of the object multiplied by its acceleration. And Newton's third law is the law on action-reaction pair. It basically states that the force that body A exerts on body B is always equal in magnitude, opposite in direction, to the force that body B exerts on body A. Right, so remember that action-reaction pair therefore always acts on two different bodies because one of the forces is on body B and the other force is on body A. Okay, so let's look at question 1. In question 1, you have a 400 kg box that is tied to a rope and is pulled out by a crane. So when you have a rope, then there should be tension in the rope if the rope is taut. Okay, T-A-U-T, if the rope is taut, there should be tension in the rope. Right, so if you're pulling the box up, then we will expect the box to be experiencing a tension in the upward direction. So go ahead and draw the tension in the upward direction. Okay, we'll let it start from the point of contact between the rope and the box. Okay, and also if it is a 400 kg box, then this box should have its own weight, and we draw the weight from the center of gravity from the box, pointing in the downward direction. Take note that for all free body diagram questions, you are expected to label the forces with their full name. Okay, so do spell out tension and spell out weight also. So gentle reminder, okay, later on when you're doing calculation, okay, always start from what is F net. Okay, F net equals to MA. Write down this equation before you proceed to do the substitution. Now part B, if the rope if the tension in the rope is 4100 Newton, what is the acceleration of the box? So you see that there's information regarding the tension, 4100 Newtons, pointing in the upward direction. Okay, and knowing that the weight W is given by mg, where mass is 400 kg. So weight will be 400 times 10, pointing in the downward direction. So you have two forces acting on this box, one up, one down. So think about how would you find F net in this case where two forces are pointing in the opposite direction. Okay, and the acceleration, which is A, can then be determined by F net equals to MA. Part C is interesting. Okay, it says the box is initially stationary on the floor. Now, if it's initially stationary, okay, what it means is originally the box is not moving, and therefore the initial velocity of the object is equals to 0. So we have U is 0 meters per second. If the tension in the rope is maintained at 4100 newtons for 10 seconds, what is the box's velocity at the end of the 10 seconds? So we think about what this statement is trying to tell us, okay? So if the tension in the rope is maintained at 4100, and we saw this 4100 newtons in part B over here, where we determine the acceleration, right? So if the tension in the rope is a constant 4100 newtons, then the acceleration should also be constant. And we have the value of the acceleration, right? So what we have in part C is a case where the initial velocity is given to you, the acceleration is constant, the time is given to you as 10 seconds, and the question asks you for final velocity. right? So there is U, there's A, there is T, there is V. Therefore, we approach this question using our kinematics equation of motion, okay? So think about what are your kinematics equation of motion and which is the equation that will allow you to determine the final velocity, okay, without knowing any information about displacement. Next part, okay, how high is the box above the ground at this instant? Okay, so at t is equals to 0, the box is actually on the floor, right? So it was originally on the floor. And then after 10 seconds, this box would have moved upwards by a certain distance, right? In other words, we are looking for what is the displacement in the vertical direction, also known as the height of the object. Okay, so again, you can approach this question with your kinematics equation. Okay, so at this point, I just want to say, okay, that Newtonian mechanics, okay, whether it's kinematics or dynamics, or even later on work energy and power, the concepts within Newtonian mechanics can always be integrated, okay, into one question. Now part D, at the end of the 10 seconds, okay, the tension in the rope is now reduced to 3,900 newtons. Okay, so what is the new acceleration of the box? So since now you have a new value of tension and a new value of acceleration, question D is no longer linked to B and C. Okay, so in this case, what we have here is a tension which is 3,900 newtons, and the weight is still 400 times 10, which is 4,000 newtons. Okay, so notice that in this case, okay, the tension is actually smaller than the weight, right? So we will expect the net force and therefore acceleration to be in the downward direction. So again, apply your F net equals to ma. Okay, find out what is the acceleration. Take note that we expect the answer to be in the downwards directions, okay, because the weight is of a larger magnitude than the tension. Part E, okay, to put the box safely onto the ground, it should be lowered with a constant velocity. What should the tension in the rope be? So when the velocity is constant, what does it tell you about the acceleration? Okay, and therefore, considering the forces acting on the box, what should the value of the tension be? Okay, please remember to present your answer with working. Okay, do not just state your answer. Question 2, a lift moves upwards with an acceleration of 2 meters per second square. Okay, sketch a free body diagram for the lift. Now, if you take a look at lifts, okay, maybe if you visit the Changi Airport Terminal 3, for example, okay, where the lift, the exterior is actually glass, okay, take a look at how the lift works. Okay, the lift actually can go up and down because of cables that are attached to the lift. Okay, so we are going to simplify the cables and just represent them with a single cable and therefore one single tension, okay, that is pulling on the lift. So over here, I'm just going to show you one of the forces. I will draw a tension that is pointing in the upward direction, and please complete the diagram yourself, okay? When you are drawing the tension and the weight of the lift, remember that part A, right, when you're drawing it, the question already tell you that the lift is accelerating upwards. So when you're drawing a free body diagram, okay, do take note of the relative lengths of the tension vector and the weight vector. Okay, which one should be longer? Think about it. Now part B again is applying F net equals to MA. I will leave you to try part B on your own. Okay, part C, as the lift approaches the highest floor, it decelerates at 2 meters per second. So as it approaches the highest floor, it's actually going in the upward motion, right? So velocity is in the upward direction. And the question tells you that it decelerates. Now, when an object decelerates, that means it's slowing down. And when it's slowing down, acceleration is in the opposite direction of velocity. Okay, so take note that in part C, this time around, the direction of acceleration is in the downward direction. Question 3, you have a 3 kg, okay, box A, and a 7 kg box B that are connected by a rope. Okay, so that is this rope over here that is connecting A and B. And then block B, okay, is the one that is being pulled by a 25 Newton force along a smooth floor. So the moment you see the word smooth floor, what it means is there is no friction. Okay, so you don't have to draw friction for this part of the question. Okay. So on the free body diagram below, mark and label clearly all the forces acting on each block. Okay, so take note that when there is a rope, then there should be tension, right? So tension always points away from the object. So at this point over here, where the rope is connected to A should experience a tension pointing away from A. At this point over here, okay, B is also in contact with the rope. Therefore, B also experiences a tension pointing away from B. Okay, these two forces here, are what we call the action-reaction pair. Okay, so this is tension T. This is also tension T. Now, if you don't want to clutter up your free body diagram, what you may do is to have a legend, okay? And just state that T represents tension. So this is then T and this is then T. Okay. All the other forces, I'll leave it to you to draw them. Okay, please remember when we are talking about all the forces, that will include forces in the horizontal as well as forces in the vertical direction. Okay, so do also draw in the weights of the objects as well as the normal contact force, okay, by the floor on the object. Calculate the tension in the rope connecting the two blocks. So for this question, okay, what you need to do is to consider the free body, or rather consider the forces, okay, on body A, and consider the forces on body B. Okay, if the two of them are connected together, okay, and B is pulled forward with a horizontal force, then I will expect the two of them to accelerate with a common acceleration. Okay, so both of them will experience a net force in the rightward direction. Okay, and that net force causes each of them to accelerate. Okay, so please consider, okay, forces on A in the horizontal direction that causes the mass of A to accelerate, as well as forces in the horizontal direction on B to cause the mass of B to accelerate. Okay, from there you should get two equations, can then solve for tension T. Next part, okay, the blocks are now pulled along a rough floor such that the blocks move at the same constant velocity. Very important, constant velocity. Now, if velocity is constant, that means acceleration equals to 0 now. Okay, acceleration is 0 meters per second squared. Okay, which means that on each of the box, the forces are balanced. F net equals to 0. Now, to solve part C, you will have to add this piece of information. Okay, please add this statement. Given that the tension in the string is 7.5 newtons, determine the friction between each block and the floor. Okay, so if you were to draw the free body diagram, then A is experiencing a tension T of 7.5 newtons. B is also experiencing a tension of 7.5 newtons. Okay. Now, because now they are moving on a rough floor with a constant velocity, okay, towards the right hand side. So each of them will experience a friction. Which direction is the friction pointing? Okay, friction should point left. Okay, leftward for each of them. I'm just going to call this FA, okay, friction by rough floor on A. I'm going to call this FB, okay, this is friction by the rough floor on B. So this is really just our rough working. Okay, question didn't ask for a free body diagram, so we'll just draw the forces in the horizontal direction to guide ourselves, okay, to answer part C. All right. So now we consider, okay, block A. When you consider block A, okay, the forces acting on block A in a horizontal direction over here should be balanced, right? Because F net on A equals to ma, right? But acceleration equals to 0 in this case, right? So F net equals to 0 Newton, right? So if that's the case, then what can you say about the leftward force and rightward force, and therefore conclude what is Fa? Okay, now let's move on to block B. When you're looking at block B, okay, the forces acting on block B, okay, let's look at B now. Okay, so you should see that there are actually three forces that are acting on block B. Okay, the three forces are the 25 Newton force that is pulling towards the right, okay, the tension towards the left, as well as the friction towards the left. Okay, so considering block B, applying F net on B equals to m0 as well. So what you should get is 25 minus 7.5 minus FB equals to 0. Right, so from there, calculate what is the friction acting on block B. Next, a man of 60 kg enters a lift of mass 800 kg. So the lift itself is 800 kg. Okay, the man over here, he is only 60 kg. Okay, the man steps on the weighing scale as shown in figure 4.1. So figure 4.1 is here. Okay, and the man is stepping on a weighing scale. Then the question says, can you sketch a free body diagram for the man? So the man with a mass of 60 kg definitely will have his own weight. Okay, and since it's in contact with the weighing scale, so the weighing scale will exert a normal contact force by the scale on the man. Okay, so which direction would it be? Remember, normal contact force is always drawn from the contact surface and then away from the contact surface. B. What will be the reading on the weighing scale if the lift accelerates upwards, if the lift decelerates upwards? Okay, so first we need to answer one question, okay? What causes the reading on the weighing scale? So I have a scale over here, weighing scale. Okay, let's take a look. How does it work? Okay, so the harder I press down, the higher the reading. Okay, the lower force I press downward, the lower the reading. Right? So what a weighing scale really measures is actually dependent on what is the force that you exert on the weighing scale. Okay, so what causes a reading on a weighing scale is actually dependent on the normal contact force by you on the weighing scale. Okay, so take note of that. Okay, so when you look at the free body diagram of the man, okay, what you should have will be the normal contact force by scale on men, right? Because when you're drawing free body diagram of men, the forces are all the forces acting on the man. Okay. So since you have drawn, okay, the normal contact force by scale on men, and you know that the reading on the scale is due to normal contact force by man on scale. So take a look at the words here, by scale on man, by man on scale. These two forces are actually action, reaction pair. Okay, so what it means is if you can find a numerical value of, let me call this n, okay? If you can find a numerical value of n, then you will know what is the reading on a weighing scale, okay? Because they should be numerically equal in magnitude. Okay, so B part 1, take note that the lift accelerates in the upward direction. And in part 2, if the lift decelerates upwards, then what it means is the acceleration is in the downward direction. Right? So this is the motion. It means velocity is upwards. And then it decelerates. It means acceleration is downwards. Okay, question 5. Block A rests on top of block B on a rough surface. So the moment you see rough, take note that there should be friction in this question. Okay, so block A is 5 kg, while block B is 10 kg. And then you have a force of 50 newtons exerted on block B. And both blocks move horizontally to the right. They have a common acceleration. This acceleration is A is 2.0 meters per second square. So the question says, on the free body diagram, okay, can you mark and label clearly all the forces acting on each block? Now, there are actually many forces, okay, acting on the blocks, especially for block B. So if you don't want the free body diagram to be too cluttered up with the names of the forces, then I suggest that you write a legend, okay, at the bottom of the free body diagram. Since A is in contact with B and A moves along with B, okay, then there should be friction between A and B. Okay, if there's no friction, A would already slide off B, okay, when B moves. So if A moves with B, it must be because there is friction between the surfaces to pull block A along together with block B. Okay, so with this in mind, okay, there should be friction by B on A. Okay, if A is pulled along with B, then what should the direction of friction be? Next, okay, because A is in contact with B, then there should be normal contact force by B on A. Okay, and lastly, of course, A will have its own weight pointing vertically downwards. You draw from the center of gravity of A. Now, next, let's look at block B. So this is the contact surface, okay, between block A and block B. So this is the contact surface. Just now we said that A, okay, should be experiencing a friction due to block B. Then by Newton's third law, okay, block B must also be experiencing a friction due to block A. Okay, and also by Newton's third law, the direction of FA and FB should be in opposite directions. So think about it. Okay, how should we draw the direction of friction FB? Oh, sorry. Okay, here, this is a contact surface, okay, at the top of B. Over here, okay, how should you draw the direction of friction at the top? Since A is in contact with B, okay, A should also exert a normal contact force by A on B, okay, originating from this contact surface and pointing away from that surface. B will have its own weight, okay. Now when you look at body B is also in contact with this rough surface. Okay, so since it's in contact with the rough surface, there should be this normal contact force by surface on B. Since the surface is rough, then as B is sliding towards the right, okay, this rough surface over here at the bottom should also exert a friction on B. We're going to call it Fs. Okay, that's the friction by the surface on B at the bottom of the block. Okay, pause the video here. Okay, do try now to draw what is the direction of the forces on A and B before you continue with part B. All right, part B. Calculate the normal contact force exerted by the floor on block B. Now, since normal contact force is in the vertical direction, what you can do is to consider the net force in the vertical direction. Okay. Since the question tells you that the object is accelerating to the right with an acceleration of 2 meters per second square, then what it means is vertically there is no acceleration. Okay, so F net equals to MA will be equals to 0. Since the question is asking you for normal contact force on block B, okay, you can just consider the free body diagram of B. Alternatively, you can also consider block A and block B as one single system together. Okay, so if you consider them together, then the two of them will have a total mass of 5 plus 10 kg. Okay, so this one whole single object over here, okay, has a mass of 15 kg, and therefore it has a weight of 15 times 10 newtons. Right? And B is in contact with the surface. So from here, you can find out what is the normal contact force on B by the surface. Okay, C, calculate the frictional force that exerts on block A by block B. Okay, so since part C is asking you about frictional force, which is in a horizontal direction, okay, for part C, we are going to consider F net in the horizontal direction. Then equals to MA. Since the question is asking you about the frictional force on block A, then it makes sense for us to consider block A. Okay, so look at your free body diagram of A. What are the forces pointing in a horizontal direction? Therefore, what is the net force on A in a horizontal direction? Okay, and that causes the mass of A to accelerate towards the right with an acceleration of 2 meters per second squared. Okay, lastly, calculate the frictional force that acts on B by the rough surface. So this time around, again, you're looking for frictional force, right? And frictional force is along the horizontal direction, right? So if that's the case, you again consider F net in the horizontal direction, which gives you MA, right? So if you consider block B, okay, F net in a horizontal direction equals to mass of B times acceleration, then you should be able to find out the frictional force that acts on block B by the rough surface.